Hi there. Thanks for joining us again. This is Space Nuts, a Q&A edition. My name is Andrew Dunkley. Hope you're well. Stick around. We have got questions from our audience. One about time in anti-gravity and the speed of time. That's always fun to talk about. We've got another question about supernova remnants, the colors of Aurora, and a light speed boost idea. This is a could I, would I, should I type of, with my spaceship, do something that might give me a light speed boost. We'll see if it works on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back once again to try and solve all your little riddles. Here's Professor Fred Watson, astronomer at large. Hello, Fred.
Hello there, Andrew. It's very good to be talking with you.
It is.
I'm sorry, I've turned into an Irishman because I
wonder what was happening there.
Yeah, because of my trip to Ireland, which is great.
There's nothing wrong with the Irish. When we were there in, would have been July? Yeah, July. They really bunged it on for us at a place called Cove. It used to be called, I think, Victoria. Was that what it was called? No. Anyway, it's where the Titanic made its last stop before heading out to the Atlantic and picked up its last groups of passengers, and some very sad stories as well. The pier where everybody got on board the boats to go out to the Titanic, because it couldn't actually anchor at port. It had to anchor outside the harbour at Cove. It's still there, parts of it. So you can still see the remnants of that old, and the White Star Line office is still there as well, which is now a museum where you can learn about the Titanic through the Titanic experience. I highly recommend that in the town of Cove, which is near County Cork. County Cork it is, yeah. Lovely place, and they had Australian and New Zealand flags everywhere and music playing, and they know how to party, those people. Yeah, terrific. Shall we do some questions, Fred?
No, I think we should just have a cup of tea.
Yeah, we'd probably have less trouble. Let's firstly get a question from Andy.
Hi, guys. It's Andy here from the UK, first-time questioner. 2 questions, both time-related. The first question, as mass and gravity are so closely related, and the higher a mass is, the slower time will flow, what would happen to the flow of time in an anti-gravity field? So, that's the first question. The second question, if a planet had life that was intelligent and was evolving and had the potential to become spacefaring, but the planet was high gravity, is the playoff between gravity and the speed of time enough that will make a significant difference to the evolution of the planet on galactic scales? Hope that one makes sense. Great program. No doubt I'll be back again.
Wow, Andy, gee whiz, you've been pondering that for a while. There's some great questions there. We'll tackle the first one first, unless you want to do the first one second, and the second. No, I don't know. Time, the effect on time, if it passes through an anti-gravity field, or just the effect on time in an anti-gravity field.
Yes. So Andy's right, actually. So what you've got is this phenomenon called time dilation. It appears that clocks slow down when you're in a gravitational field. They only appear to be slowed down to outside observers. To you as the person in the gravity field, it makes no difference. The clock's just ticking at the same speed as it always did. But to an outside observer, your clocks are ticking more slowly. If there was such a thing as an anti-gravity field, and we have no knowledge of anything like that at the moment, although people have worked very hard to try and demonstrate anti-gravity. As you can imagine, it would be a very useful thing to be able to harness. If you could have anti-gravity, in other words, something that actually repelled rather than attracted, yes, or at least, no, let me put it another way. It's not repulsion. It's reducing the effect of gravity, I think. Anti-gravity might reduce the effect of gravity. And it could, if you reduce it beyond zero, it could produce a repulsion. But that doesn't really matter for this argument, because what happens is, yes, relativity says that time would actually speed up. Time, as I said, to the person in the anti-gravity field would keep on ticking away as normal, but to the outside observer, the time would appear to be passing more quickly.
Isn't it the same effect if you are falling into a black hole? What you're seeing is happening in real time because you're living your life like you do anywhere. But to the observer, you would be, a completely different bucket of fish.
That's right. Time slows down. Everything appears more slowly. And when you cross the event horizon, you're sort of frozen on it.
Yeah.
Which means that
weird, isn't it?
Event horizons are always all splattered with things that have fallen into the... Maybe.
Yeah.
Hard to imagine.
It's like the front of a car.
A bit like that only
in summer.
White hot, yes.
Yep. I think this was portrayed quite well in the movie Interstellar, where they had to go down onto a planet that was under the effect of a black hole, and every hour on the planet's surface equated to 7 years back on the spaceship. They did portray that quite well. That effect.
Yeah.
Okay, so there's no such thing really as an anti-gravity field, but he'd be right. The effect would be...
Yeah, that's right. But the second part of Andy's question...
Yes, high levels of gravity and its effect on the speed of time.
Well, what he's saying is, if you had a planet... or if you had a civilization working in a very high gravitational field, would that mean that they would evolve more quickly and things would develop more quickly? And I suppose the answer is yes, but only to an outside observer. To the people doing it, it would be just the same. So yes, maybe if our planet had a hugely different gravitational field from what it does have, seen from the outside, we might look as though we're evolving more quickly and developing technology more quickly. But to us, it would be just the same as if we had, a lower gravitational field.
This would complicate the search for intelligent life, wouldn't it? You might find a planet and go, "Hey, something's going on there," but it's in a high gravity environment, and maybe it was happening some time ago, but it's all over Red Rover. I mean, I don't know. It's a head scratcher. Or here's one: you do find a civilization living on a planet, and you land to say hello, and then you take off again and find out that everyone at home's dead because you've been gone 500 years, but you were only gone a week.
Yeah. Well, there's that too. That's right. Yeah. That's special relativity. That's the one. The relativistic difference in time, because you're traveling at speeds near the speed of light.
Yeah. I mean, it happens on Earth. They've done those tests with highly sensitive clocks and tested them at different altitudes, and they've come back and went, "Oh, look, there's 1,000th of a second's difference in their performance." So that we've moved through time. I read a story the other day, Fred, which I wish I'd kept it, about a cosmonaut, I think it was, who'd spent so much time in space that they estimated that he was actually slightly ahead of time than everybody else. And I can't remember the details, but it was really fascinating. They've released a paper about it. I'll see if I can find it.
Yeah, that'd be interesting.
I might do that while you answer this next question. Thank you, Andy. I love that idea, though. Keep them coming. Now let's take a break from the show to tell you about our sponsor, NordVPN. Now, I think we'll all agree that exploring the universe is thrilling, but exploring the internet without protection, that's a black hole you don't want to fall into. Sorry. As a Space Nuts listener, we have an exclusive deal for you so you can stay protected, and that is NordVPN. It's the fastest, most secure way to browse the web. With NordVPN, you get next-level encryption, blazingly fast servers around the world, and zero tracking, so you can stream, shop, or scroll safely. It's the tool I personally trust when we're diving into the internet, and we want to give you peace of mind. I've used it overseas several times. I've used it at home. It works and it is seamless. Head to nordvpn.com/spacenuts for an exclusive deal just for Space Nuts listeners. Big savings plus 4 months extra, absolutely free. Don't surf the cosmos unshielded. Secure your digital universe today with nordvpn.com/spacenuts, and don't forget their 30-day money-back guarantee. Go to nordvpn.com/spacenuts.
3, 2, 1.
Space Nuts.
This question comes from Mark. Hi, Andrew and Fred and team. My name is Mark Turner and I live in the south of England. I'm sorry about that. About 5 minutes from Patrick Moore's house as a point of interest. Wow. I've been listening now for just over 3 years and always look forward to Thursday lunchtime when I sit down and listen to you guys. Sorry, we were talking about toilet stuff earlier. I hope that didn't mess you up. My question is, it's generally accepted that all of the heavy elements were produced in an even larger star than ours that went supernova, which leads me to this. Can we still see the remains of the star that made us in the night sky, or do we know at what point in the night sky the star would have been by turning back the cosmic time clock? Keep up the great work, Mark. What do you reckon about that one?
So the answer is no, because the what we call the interstellar medium, the gas between the stars, is enriched in its chemical abundance, the amount of heavier elements that are in it. It's enriched over time because of supernova explosions, stars that have detonated and gone through this high temperature process where you get heavier elements created. And some of the heavy elements we now know are created in neutron star collisions, but that doesn't matter which it is. The bottom line is that it's the general interstellar medium that is enriched. So you've got an explosion that takes place, and over millions of years, the debris from that explosion just gets absorbed into the clouds of gas and dust that are then going to form later generations of stars. So there's really no way that the remnants of the star that gave us the heavier elements, there's no way that we can pinpoint that. It may be that some of the supernova remnants that we see, and we see many around the sky, that some of those were responsible for some of the stuff. They were probably responsible for enriching the interstellar medium closer to them than we are. That's kind of the point I guess I want to make. The debris that gave us our enriched interstellar medium is probably long dissipated, and we could not identify it with any of the known supernova remnants because they're still enriching their local environment, if I can put it that way, because they're still intact structures. They're expanding and dissipating, but we see them as intact structures. And so the debris that made us 4.6 billion years ago is basically is nowhere near. It's nothing to do with them. And partly because those explosions took place more recently than the 4.6 billion years ago origin of our own solar system. So the answer is no. We can't identify those remains. And turning back the cosmic time clock, we can do that, but we can't do it in the sort of detail. I mean, we can do it in physical modeling sense, we're not looking at anything unless we're looking at things at great distances where we are looking back in time. But for the physics that you use to model the universe, we can't wind back the clock in enough detail to see where these objects exploded. They may be, many, many thousands, tens of thousands of light years away from where we are now. All they did was enrich the medium around them, and that's where we found our own solar system being formed. So we can't look back in time in that regard.
Okay.
Thank you, Mark. By the way, I was a pretty regular visitor to Patrick Moore while he was still alive, so I know that house well at Chelsea. It was called Farthings. It was a lovely house, actually. And when I used to visit him, he was always very welcoming and always glad to show me around.
Wonderful. Wow, lucky you. Yeah.
Yeah.
Now, just to sort of draw on Mark's question, so he's right about a supernova creating the heavy elements.
Yes.
So how do they end up being a part of our planet? Is that because the supernovas created the spawning ground, or being, we've run through it? How does that work?
Yeah, I mean, it's what I was saying. Basically, you get a supernova explosion, which sends shockwaves out. It sends enriched gas out, and that gas gradually diffuses into the background, what we call the interstellar medium, the gas between the stars. It's very, very rarefied, but that's where that stuff ends up. And as you then get concentrations of that gas into clouds of hydrogen, mostly hydrogen, but other elements as well, because it's been enriched, then that is what would form the next solar system. And so that gradual process of stars forming, exploding, enriching the interstellar medium, then interstellar medium creates other star systems which do the same thing. It's why, as the universe ages, you're going to get an enrichment of the number of quantities of heavier elements that there are within the universe. And that's actually one way that we can measure the ages of stars, by how much of this stuff they've got in them. Because when they were formed, the universe would have been at a certain point of enrichment. That point is fossilized, if I can put it that way, in the star itself by the chemical composition that it demonstrates.
Okay, very good. It's a law of diminishing returns, though, isn't it? Eventually, all of this is going to stop happening.
Yes, that's right. Eventually, the universe will die because of that, because there won't be any more, and there won't be any gas in which to create supernova explosions, which is the raw material of stars, hydrogen gas. That will all be used up eventually, and we'll have what used to be called the heat death of the universe, unless it starts collapsing on itself again.
Well, yeah, I mean, there's all these terrible, perilous things that are going to happen, but it's not going to happen next week. The week after, maybe, because we're on holidays.
If we're lucky, over the week after, yeah, that's right.
Yeah. Thank you, Mark. Great question. Now, that thing I was trying to look up, I can't find the exact story, but I found something that kind of explains the concept. Apparently, for a 6-month mission on the International Space Station, an astronaut ages 0.005 seconds less than they would on Earth. So this particular cosmonaut that I'm talking about apparently has spent so much time in space that he's actually, I think it's 0.22 minutes younger than he would have been had he not gone into space.
It's 5 seconds rather than minutes, yeah.
Oh, 0.22 seconds, yes, exactly. Yeah. So I read it last week. I meant to send it to you and I completely forgot. So, but that's the guts of the story. This is Space Nuts. Andrew Dunkley with Professor Fred Watson.
Space Nuts.
We have a question from one of our regular contributors. This is Casey.
Hi guys, this is Casey from Colorado. I just saw Red Northern Lights and it was really incredible. I was hoping that you could please explain why auroras come in different colors. I hope you're both well, and thanks for the podcast.
Thank you, Casey. Casey sent in a few questions in recent times, and we're more than happy to answer. She comes up with some interesting ideas. I just thought this was a good question to answer. I know we've talked about it before, but there's been some great auroral activity of late. And even in parts of Australia where you just don't see them, they have been absolutely stunning. Even as recently as a week or two ago, we had some fabulous photographs coming out of many, many parts of southeastern Australia. And it prompted a thought in my mind that the aurorae we see here generally are pink. But when you see photos up in the Northern Hemisphere, when you're practically underneath them, they're green. And I'm sure the colours can vary into many areas, Fred. I mean, you've taken tours on these to see these things. You've seen that, like, this is boring for you, but
it's never boring, actually.
No, I can imagine it wouldn't be.
Just always spectacular. But you're absolutely right. So when we're up in Alta, which is far northern Norway, or Kiruna, which is far northern Sweden, or Abisko, which is also far northern Sweden, and looking at the aurora, you're basically standing underneath it. And so you see the aurora as it really is. And you've got lots of colours in it. But the pink and red aurorae are typically seen when you're a long way from the action. And the green, the bottom line is the green is
talking redshift?
No.
But we're talking atmospheric.
We're talking emission line spectroscopy.
Oh, okay. Well, I never would have thought of that.
Yeah. So the pink and red aurorae, you'd see them if you're in the northern hemisphere. You'd see them on the northern horizon. In the southern hemisphere, here in Tasmania, you see them very often down in the south. Usually, the green part is below the horizon. It's it's too far over the Earth's curvature to see, and that's why you only see the red. And that's a clue to what's happening here. So what you've got is the atmosphere being excited by radiation from the sun. These subatomic particles charge out from the sun. If you've got a solar flare or something like that, they're going at typically 1 million kilometers an hour. So they take a couple of days to get here. And then they're sort of funneled down the Earth's magnetic field lines, and they're most concentrated near the magnetic poles, which is why it's around the magnetic poles that you see most aurorae. This is a sort of simplified version of the story. Yeah. But what happens is these electrons, and they're accelerated, they're quite high energy. They hit atoms of oxygen and nitrogen in the Earth's atmosphere, and they make them glow. And the important thing here is that those atoms of oxygen and nitrogen, and actually they're molecules as well, O2, which is a pair of oxygen atoms, or N2, which is a pair of nitrogen atoms, they behave differently at different pressures. And of course, as you go up through the atmosphere, the pressure gets steadily lower. So the most common one is the green light, and that's when you've got oxygen being excited to emit this green color. It's what we call a spectrum line. It's a particular wavelength, which means it's a particular color, but it's green. And that works for pressures that you see between about 100 and 200 kilometers above the Earth's atmosphere. Above 200 kilometers, the pressure is lower, and the green line doesn't form, or the green light is not formed. It's actually quenched, and there is a different atomic process that gives rise to red light. 630 nanometers, if I remember rightly, is the wavelength. So you get this red light, which is still oxygen, but it's oxygen at a lower pressure than what comes out from the green. So between 1 and 200 kilometers, you're going to see green aurorae. Above that, you're going to see red aurorae. And that's why we only see the red ones if you're looking from Australia, because the green is way below the horizon. If you've got a really powerful stream of subatomic particles, then they will penetrate below 100 kilometers. And that then excites not the oxygen, but the nitrogen. You get what's called molecular excitation. Nitrogen molecules start emitting light, and they emit in several different colors, like deep blue. There is different red. There's sort of greens, and all those mix together to give you something like a purple. Often in a bright aurora, you've got the green auroral curtains, and below that there might be a purple layer as well. And sometimes the colors are so mixed that it turns white, that you actually get a white bottom edge to an aurora. And then you know you've got really high energy electrons. And then
You've always seen one of those?
yes, I have. I've actually, the very first time we went up there, I've got photographs taken from a place called Lyngenfjord in northern Norway. A very dark site. It was a wonderful place to see the aurora from. And yeah, there were definitely white bottoms on my auroral curtains.
Wow.
What I was going to say was that's the basic story. But in reality, you get these things all mixing. And so sometimes you do get pinks, and you can actually get some quite odd colors, almost browns, actually. I took some photographs at the beginning of this year in far northern Norway and later in Greenland, where the colouring was almost like a brown colour rather than the reddish that you expect from high altitude aurora. So it's the way the colours mix that give you the different effects. Plus, you've got to add to that the colour response of your camera as well, which can sometimes tell you, give you falsehoods, because the camera itself is basically tuned to take photographs of everyday objects. It's not really tuned to take photographs of things that are emitting only on one wavelength, which the aurora does.
Yes, I know. Although while we were up there, northern parts of Europe, Norway, Greenland, Iceland, people did try to take photos of aurora, and a couple of them were successful. I was not. I did see one, but it was summer.
Yeah, summer's that's the problem, because there's still so much twilight there. I used to cart around a proper digital camera with me and a tripod to do all these long exposure photographs. But to be honest, now with a smartphone, they are so sensitive you can hand hold them and get really fantastic auroral photographs. Which blew me away the first time I did it, which was the beginning of this year. I tried it a little bit on the previous trip that we had up to northern parts, which was in Canada, actually. But this time, at the beginning of this year, in Norway, Sweden, Iceland and Greenland, I just held the smartphone up, and, well, I've got more photographs than I know what to do with, and they're all dramatically good. The smartphone is such amazing technology.
It's changed the world. In many ways, particularly when it comes to photography. It was the old Canon Snappies and all those that we used to have with film in them. You got one shot at it and you didn't find out if it was any good for a couple of weeks.
Yeah, and the odds are that it wouldn't be, because this sensitivity of film is so much lower than than the sensors that we now use for images. That's the bottom line. Yep. Yeah,
the gear is good now. Makes everybody a professional. Well, not quite, but you know what I'm saying.
Talk to a professional photographer and they won't actually agree with that.
No, they work hard. Thank you, Casey. Great question, and good to hear from you again.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our final question today. Hi, guys. Love the show, etc., etc. He doesn't bandy around much. He's straight to the point. An idea just occurred to me. Mass increases the faster you go, becoming infinite at the speed of light. So, if it were possible to accelerate particles up to relativistic, I hate that word, relativistic speeds in some compact device, and then throw them out of the back of a spacecraft, would the acceleration increase because you're throwing more mass out the back? Yeah, I did that the other day. It's not pleasant. Kind of an ion engine on steroids. I'm envisioning some kind of small particle accelerator powered by a nuclear power source, preferably fission. Any thoughts? Absolutely welcome. Many thanks and keep up the great work. Lee in Sweden, not to be confused with Swede in Leeton.
Oh, okay. Really?
Yeah, that's somebody else. No, Lee in Sweden. So, okay, so he's got a particle accelerator on his spaceship, and he's accelerating the particles up to relativistic speeds, and then he's shooting them out the back of the spacecraft. Bigger mass, whatever. Can it accelerate the spacecraft?
Yeah. All right. I'm going to read what I've just brought up on the screen in front of me. Relativistic mass ejection in ion motors is not a current technology, but a theoretical concept for future propulsion, where ions would be accelerated to speeds approaching the speed of light. The relativistic aspect refers to the effect of special relativity, where an object's mass appears to increase as it approaches the speed of light, making it harder to accelerate it further. This would require extremely high energy inputs and would involve complex physics, unlike current ion thrusters that use less energetic, but still very high ion ejection velocities. That came from AI. So how's that?
Yeah, well, I mean, AI can be very useful.
That's kind of what I
so steer you up the wrong path. It kept getting done. Yeah, like I had to make some pretty significant inquiries last year, early this year, whatever, about a housing situation, and it just got it so wrong constantly.
Yeah.
But yeah.
So what I've just read out is putting nicely into words what I was going to say, but it's putting it rather more nicely than I would have put it. So there you go.
Yeah. All right. So the concept of creating engines that can do these kinds of things is real in science, but only to a certain degree.
Yeah. My only worry about it would be, and I guess this is what, the complex physics bit was, you've got different reference frames. You've got the reference frame of the spacecraft. You've got the reference frame of the flow of charged particles coming out the back of it, and you've got a stationary reference frame, and the mass looks different to all of those. So that will be my only worry about that, and it's the thing that I would like to go a bit further into it rather than rely on AI. But the basic principle, I think, is quite right. But I'd have a caveat about just watch out for your reference frame, if I can put it that way.
Yeah. I've been toying with AI just to sort of get some concepts in my head about, I mentioned, I don't know if it was this podcast or the previous one where I'm writing a new book, but there's some concepts I wanted to include, but my brain wouldn't go there. So I did use AI to try and learn what I needed to learn to make the thing work the way I wanted to in the story. It's very clever when you want to do things like that. So,
did it help?
Yeah, very much.
Oh, that's interesting.
Yeah. In fact, it sometimes gave me way too many concepts. I only wanted one, but it gave me 10. And I'm thinking, oh, hang on. That's all good stuff. I can't use it all. So I had to pick. But I found it very useful. But if you use it the right way, it's a great tool. But for general information, sometimes it can just hit you're throwing a dart and hitting that metal thing around the edge.
Oh, right, okay.
Because it's throwing information back at you that's too generic, I suppose.
Yeah.
Sometimes. I think when it comes to AI, you've got to know how to use it to get the best out of it. Otherwise,
maybe that's right. Yes. Otherwise, it's dangerous.
Yeah,
and
absolutely.
The wrong path.
Absolutely true. Yeah, I have found it very handy for I've had a few photos over the years that I've wanted to keep, but they've not been really good photos, and it's been really good at cleaning them up. Taking out some of the there's one particular photo that I really love, but it's grainy.
Yeah.
So you just upload the photo and say, can you? I can't remember the terminology I used, but can you do this? And it takes like a minute or two to recalibrate the photo, and then it gives you its result. And I had a couple of big hits with that worked out well, but I've had a couple that didn't.
Yeah.
Because it had to try and fill in spaces because of the graininess of the photo. Okay. And what it filled them in with actually changed the subject too much, and I didn't like it. If that makes any sense at all. But, I do find it useful, but it's not a perfect science, and you've got to keep that in mind. Lee, thanks for your question. Did we finish with Lee? I'm pretty sure we did. Yeah. Good on you, Lee. Hope all is well in Sweden, and I'm sure you get to see lots of Aurora too, you lucky duck. That's it, Fred. We are finished. Thank you.
You're welcome. I've enjoyed getting my mind bent around some of those issues myself. So thank you, Space Nuts listeners. You keep me on my toes.
Yes, they do, don't they? If you would like to send us a question, you can do that through our website, spacenutspodcast.com or spacenuts.io, and you click on the AMA link at the top of the homepage and just fill in the blanks. You can send us your text questions that way, or you can send us an audio question if you've got a device with a microphone, and just remember to tell us who you are and where you're from. Most people do these days. Or you can send us questions via YouTube. We've been getting a few of those, and sometimes they just turn up on social media. It doesn't matter. We'll get to them. Although on social media, the audience tends to deal with them for us. So not many of them filter through. But keep those questions coming. That'll all be good. Fred, we'll see you next week. I think it'll be our last couple of programs before the Christmas break.
May well be. That's right.
All right. We'll catch you then. Thanks, Fred.
Oh, sounds good.
And thanks to Hugh in the studio, who went supernova on us because he's got a lot of heavy elements and he's gone to see a dietitian. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.